Welcome to Design World's How to Calculate series, where you learn how to apply the most important equations for sizing, selecting, and comparing linear motion and motion control products. In this session, we'll learn how to calculate slip in an AC induction motor.
When an AC induction motor is started, the supply voltage creates a magnetic field in the stator, which induces current in the rotor. The induced current in the rotor also creates a magnetic field, and the interaction of the stator and rotor magnetic fields produces torque and causes the motor to turn. The speed of the stator's rotating magnetic field is known as the motor's synchronous speed. The synchronous speed in RPM can be found by multiplying the frequency of the voltage, which is typically 50 or 60 Hz, by 120 and dividing by the number of stator poles. One of the fundamental characteristics of an AC induction motor is that the rotor magnetic field, and therefore the rotor shaft, spins at a slower rate than the stator's rotating magnetic field, or synchronous speed. This difference in speed between the rotor and the stator's magnetic field is known as slip. Slip is expressed as a percentage of the motor's synchronous speed and can be as low as 1% for high horsepower motors and up to 6% for fractional horsepower motors. Note that the rotor speed is also called the rated speed or full load speed, which is the speed of the rotor when the motor is fully loaded and operated at the rated voltage. Rated speed is typically shown on the motor's nameplate. Slip allows the motor to produce torque. The higher the slip, the higher the torque production, but also the lower the motor's efficiency in most cases. This is because slip is essentially energy loss, which is converted to heat that can damage the motor and cable insulation. Because of this heat, the motor can't produce full torque at low or zero speed in continuous operation. One way to address slip is by using a variable frequency drive, or VFD, with closed-loop vector control. This control method allows the VFD to adjust the torque by controlling the magnetizing and torque-producing components of the stator current, so the drive can provide good torque control regardless of speed, including down to zero speed. And in some applications, slip can be a benefit. For example, when two or more motors are connected to one drive, motor slip can be used to prevent one motor from taking a disproportionate share of the load. As one motor experiences increased load, its rotor speed slows down, increasing slip between the rotor and the stator. The second and subsequent motors, which are connected to the same drive, will also slow, allowing them to take on the additional load. While using the motor's natural slip is a simple method of load sharing, it's imprecise and not reliable at high loads. For more precise load sharing, some AC drives include a function referred to as droop control, which manipulates motor slip based on the amount of current each motor is drawing. For more information on AC induction motors and other motion control topics, visit motioncontroltips.com or designworldonline.com. Thanks for watching.